Okay, hi. My name's S.Blunt. My pronouns are she, her, hers, and I'm a fourth and final year grad student at Caltech. And in the fall, I'm going to be starting as a Sierra Fellow at Northwestern. So it takes a village to raise a PhD student, and I want to throw up all of the collaborators that have worked with me on this particular result that I've shown you. And I also want to put the beginning of the acknowledgement section of my paper, because I think there are a lot of people that have helped me understand what I'm about to talk to you about, and I want to make sure I get to acknowledge them too. I in particular want to acknowledge Chaz Beichman and Alejandro Suarez Mascareño for their collaborativeness, help, and patience throughout this whole process. Okay, so I'm going to talk to you today about overfitting affecting the reliability of EPRV mass measurements of V1298Tau. And I put a little asterisk next to reliability because I'm not going to try and prove that the published masses are or are not correct, but I am going to try and advocate that we need a predictive model before trusting the masses. And I'll talk to you a little bit more about what that means. And I also want to make sure I thank the organizers and the hotel staff. This has been a really, really fun conference, and I've learned a lot, and I really appreciate it. Okay, so first, a little bit of motivation. So V1298Tau is a very young star. It's about 20 million years old. It's not even on the main sequence yet. So why might we want to study it? And one main piece of motivation is that the masses of young planets give us clues about how they formed. So if you're able to measure precisely the age, radius, and mass of very young planets, you can distinguish between formation models. So I'm plotting here from, at this point, a pretty old Marley et al. Paper, the difference between the cooling tracks over time of giant planets that form via hot start or via cold start. And this is the difference in their initial entropy. So we can use the current day characteristics of these planets to backtrack how they got there. Another piece of motivation is that massive planets around young stars are really good analogs for the Earth-Sun problem. And what I mean by this is that the ratios of signal to activity are about the same. I realized immediately before I went on that I'm off by a factor of 2, but you know, what's an order of magnitude among friends? Yeah, and 800 meters is not a joke. That's the scale of the activity on the system. We're looking for a 20 meter per second planet signal. So before people point out to me all of the differences between activity on young stars and older stars, that's definitely true. But this ratio, I think, is true. We're going to have to find signals that are at this ratio around planets with this, around stars with this level of activity. So if we want to practice, we have young stars that we can practice on nowadays. Another good argument for studying young stars is that we can isolate spot activity on young stars. And what I mean by isolate is that the spot signals are so much larger than any other signals on young stars. 800 meters per second is so much larger than your systematics of your instrument. We don't expect like convection signals to be larger or oscillations to be larger than they are on solar type stars. So you can be sure that what you're looking at is actually spot activity. Okay, so let's talk a little bit about V1298Tau specifically. This is a moving group member, a young moving group member. So it has a pretty precise age estimate of 20 million years. It's at a distance of 108 parsecs, and there are 4 transiting planets discovered in K2 by Trevor David et al. That are between 0.5 and 1 Jupiter radius. And I wanted to show you what the RVs of the star actually look like, and make sure you look at the y-axis. This is in meters per second, so they're 800 meter per second deviations. So there's a huge amount of activity. Suarez Mascareño et al. 2021 came to a surprising conclusion by doing a model, a joint model of the activity and the Keplerian signals around V1298Tau. They made mass measurements and came to the conclusion that the V1298Tau planets must have rapidly contracted after formation. So the 2 V1298Tau mass measurements are at sort of the bottom the bottom of the top right of this plot. You can see V1298Tau B and E, and field exoplanets are plotted in the background on this diagram as blue bins. So you can see that B and E are more dense, not only than most of the field exoplanets, or than most of the field exoplanets that we know of, which is pretty surprising given that these are super young. So we would expect them to be much less dense than field exoplanets. But the conclusion was that they're actually like on the denser side. So I'll get right to the point of my paper, which is that the preferred model in the SM21 paper is not predictive. And what I mean by this is that the model doesn't predict new data points. So there's a lot going on in this figure, and this is sort of the main point of the talk, so I'm gonna go through it slowly. So in the gray model in the background is the preferred model of this paper. So you can see there's a lot going on in this model. There are Keplerian signals, there's a Gaussian process activity model, and all of that comes together to jointly model the observations of different instruments. And we've got 3 different instruments of data that are shown in the background. On the bottom is residual, so this is data minus model. So you can see that the HARPS north points in particular have a pretty narrow spread around the residual equals 0 line. And an important piece of context here is that the SM21 preferred model was trained and conditioned on HARPS north points. So you can think of those as the in-sample data points. The other 2 instruments have a much wider spread, and this is indicative of poor out-of-sample predictiveness. So I'm guessing that a couple of people in the audience right now are thinking, well, they're different instruments, they have different band passes, we would expect them to have different activity signatures. I think there are a couple of different ways to answer that question. One is that we also did this just for HARPS north points and found the same thing. So it's not something specific to it's not something specific to the different instruments. And there's other reasons that I'm happy to talk about in questions. Yeah, so I think the other thing to point out that I didn't point out yet is that the gray bands in the background are 1 and 2 sigma Gaussian process uncertainties. So you can see that where there are HARPS north points, those black points, the Gaussian process uncertainties are pretty small, meaning that the model has a good idea of what the data points are expected to be there. Where there aren't HARPS north points, there's much larger uncertainties. So to the left of the plot, where we've got a bunch of high-res points, but no HARPS north points, there's wide uncertainties in the GP model. So it's not necessarily a problem here that the high-res points have a wide spread about the mean, but where there are simultaneous or near simultaneous data points, you can see that there's a lot more spread in the expected and actual positions of the RV points. Oh yeah, those are the uncertainty bands. Okay, so I want to make something clear that this is not intended as a takedown, meaning that I'm not trying to say this is something that this paper did incorrectly. I think this paper did an excellent job. There are 2 main points. One is to show you that we can't model V1298Tau with state-of-the-art techniques. There's something beyond our understanding. And 2, to convince our field to do cross-validation. So I think it's sort of immediately clear when you plot the predicted and actual data points for the V1298Tau model that the model is not predictive, and so we know something is going wrong. Oops. So yeah, don't get me wrong, I love Gaussian processes, but Gaussian processes are still models, and models can be wrong. I am going to spend the rest of the talk talking about some things that I think might be going wrong or weird in V1298Tau that's causing this model to not be predictive. So first, I want to briefly review the preferred fit of the SM21 paper. So as I said, they very thoroughly characterize the V1298Tau activity signal using state-of-the-art techniques. They used a Gaussian process with the Celerite package and jointly constrained hyperparameters for this Gaussian process using RVs and photometry. They did a huge suite of model comparisons using Bayesian evidence, and then also did injection recovery tests to validate the choice of activity model. So I know a lot of papers that didn't do this much stuff. And so why is this not working on this star? I don't have proof, but I have theories. The paper that I wrote about this goes into 4 particular things that I think might be going wrong. Since it's a 15-minute talk, I'm going to talk about one of them. A source of unmodeled stellar activity. The unmodeled source of stellar activity that I think might be causing the issue for V1298Tau is that V1298Tau has a really strong differential rotation signal. And the idea here is that all stars differentially rotate. They rotate faster at the poles and slower at the equator. On the sun, this is a difference of 25 days at the equator and 35 days at the pole. So if you have spots or active latitudes at different latitudes, they'll have different rotation periods. And you can see this by eye in V1298Tau. The purple points here are K2 data. And I've shown over this the envelope of a very simple beating model of, in this case, two different periods that are coming into and out of phase. So you can see the signal get bigger when the 2 spots come into phase and smaller when the spots come out of phase. So if we think it's challenging to model an activity signal on a star that has 1 rotation period, imagine doing it on a star with 2 or 3 or 10 rotation periods. And not only that, the periods are changing in time. So this is just a Loam-Scarville periodogram of different photometric data sets of V1298Tau. And you can see, first off, the multiple very closely related rotation periods. And second of all, that these rotation periods are shifting between all of these different photometric data sets. So this sucks. This makes it really, really hard to model this system. So I bring this up not because I have proof that this is ultimately the thing that's wrong with V1298Tau, but because I think this is something we need to think about as a community, and we haven't thought about that much so far. So I have a couple of takeaways, and then I also have 2 more slides, so don't clap yet. First, that young planets are formation probes and young stars are activity touchstones. Second, cross-validation is a powerful and often very interpretable tool for assessing model performance. And I think especially for Gaussian process models is something that I would encourage us all to try to use. And last, that the V1298Tau preferred fit is not predictive. And this could be related to unmodeled stellar activity, in particular the star's differential rotation. Okay, so my last 2 slides. On the first day, Suvrith made a point that one of the things we should do at this conference is talk about how we want to recruit and maintain the best talent. And I want to offer my opinions on this. First, I think we need to financially support undergrads, grad students, and postdocs, and particularly support unions. I think it's important to regularly ask students for feedback, financially support existing organizations for early career and minoritized researchers in particular. If you haven't heard of Black and Astro, you should go check them out and write them a check. Learning about trauma-informed teaching and mentoring, and also learning about and financially supporting the Native people whose land we're on. So for example, we're currently standing on the land of the Chumash people of Santa Barbara. When I came here, I made a donation to this website. I would also encourage everyone to at least check it out. And then last slide, I have some advertisements for some things that, yeah, some fun things. The first is Radval, which I'm one of the core developers for. In particular, the newest version of Radval that's going to come out in a couple of weeks has a new and improved Gaussian process treatment, so I'd encourage you to check that out. I'm also a lead developer of Orbitize, which is a tool for fitting the orbits of directly imaged exoplanets And I also encourage you all to check out Code Astro, which is a week-long software development workshop for astronomers at all career levels. Okay, so I will go back to my quiz and take questions. Thank you for your attention.
Let's make time for one quick question for Sarah. And if we could get the next speaker on the way.
Thanks very much for the talk. I think I'm misunderstanding something conceptually here. How does not accounting properly for differential rotation give you the wrong RV between different instruments where you're observing at nearly the same time?
So it's not that it's that the model isn't able to predict. So let's take away the different instruments just for conceptual case. So, because this is true for HARPS North too. So imagine that you model your data points, but if you hold out 20% of the data points, the model doesn't predict those new data points. So the idea is that if your model only contains a single rotation period, but there are actually multiple rotation periods, the RVs can sort of jump up and down a lot more than you sort of expect if you only have one rotation period. So this combined with the fact that we have sparse sampling in the RVs relative to the actual rotation periods means that you can not predict intermediate data points. Does that help?
Maybe. Let's chat more over.
Okay, sounds good.
Let's thank Sarah one more time.